All right, here we go. The final lesson of the course. So we're going to look at intersection between planes. So we're going to start with intersection of just a plane with two planes, but sort of that's just kind of a stepping stone to get us to the real problem, which is going to be the intersection of three planes at the same time. So that's sort of the big thing. This is the skill that I wanted to get to in vectors because we're going to learn how to what's called row-reduced matrices, which is pretty fun thing to say. But basically, it's the one skill that I kind of remember doing all the time over and over and over in my first linear algebra class in university. So I did want to make sure that you got a taste of it before you went, in case that you do end up taking this type of course in university. So here we go. So we're going to think about two planes and how they can cross. So you can try and figure out the cases. So look at your desktop as like a flat surface to be one of the planes, and then maybe use your lesson sheet as the other plane. But again, keep in mind that they'd extend forever and ever in both directions. See if you can come up with the ways that they can or cannot intersect. And what you should find is that there are three cases. So if they're going to cross, one plane's going to look like that. The other plane's going to look, something like that. Keep in mind they'd kind of extend off in the other all the way through and all the way through. Something like that. But what we get is we get a full line of intersection. Intersection. There we go. So they can cross as a full line. They can not cross at all, so they could be parallel planes. Not crossing at all. It's a great picture. Or I could, as I'm wont to do, give you one plane, give you the other plane, and they're actually the exact same plane. So parallel planes would be no solution. This would be infinite solutions because there's a whole line of points. This one would also be infinite solutions, but they'd look different. So the third case would be the full plane. The first case, we'd have to find the line of intersection. So how we do this, the way we kind of organize the information is with something called a matrix. And so a matrix is just sort of a box of numbers. So if you've taken data management, you might have seen matrices before, but we're going to do very different things with the matrix. It's just a way to organize information. So how we have to do this, if the d value is on the left side, which is sort of the typical way that it is, I want you to take a second and move that over. So move the -7 over, make it +7 on the other side, and make that -12 on the other side. So have the x, y, z stuff on one side, and the d value actually move to the opposite side of the equation. Well, actually, before you even do that, we should see if we have to do any work. So the first normal vector is 3, -2, 1. My second normal vector is 2, 4, -2. And we see that these are not scalar multiples of each other. So now, in this case, they'd be heading in the same direction if they're parallel. Obviously, if it's the same plane, they'd be heading in the same direction. So as soon as we see that the normal vectors aren't scalar multiples, that the normal vectors are not heading in the same direction, we know that our answer for two planes is going to be a line of intersection. And so we jump in, we move the d value to the other side. That's when I would do that, actually, is now. And then we're going to turn that equation into what's called a two-row matrix. So 3x minus 2y, 1z, and then where the equal sign is, you put a vertical line, and then a 7. And then 2, 4, -2, -12. So that's going to be our matrix. So it's just a way to organize the information. When you have that vertical line in there, it's actually called an augmented matrix if you want some fancy words. And what we're going to do is we're going to row reduce this matrix to get to our line of intersection. So this all sounds kind of crazy, but basically I'm going to jump down to the allowed operations when row reducing a matrix on the next. So our allowed moves, what we're allowed to do to these matrices, it's basically, if you remember back to grade 10, you had two ways to find points of intersection. You had substitution and elimination. The matrix operations, it's a way to do elimination. We're actually doing elimination instead of substitution. And the matrix just helps you organize the information. And again, this is something that I had to do all the time in my first linear algebra course. So I want to make sure that you understand these operations. So you are allowed to swap the order of rows. We can swap rows around because that's just like writing the first equation first and the first equation second and the second equation first. The order you write the equations doesn't really matter. Sorry. I should say add or subtract a row to another row. So I can take row 1 and add row 2 to it, and that'll become my new row 1. That's something we're allowed to do. I can multiply a row by a scalar because each row is just representing an equation. So if I multiply the whole equation by 2, it doesn't change the overall equation. So that's something that we're allowed to do. And the thing that we're going to do most often is combos of 2 and 3. So we're going to multiply by scalars and then add or subtract. Now this all seems very abstract, but with the 2-row matrix, our goal is to get it to look like this. 1, a number, a number, and a number. And then below the 1, a 0, and then a 1, and then a number, and a number. So that's our overall goal. Sort of what I'm going to call the robotic order. So if we are just robots blindly going through this, sometimes there's better ways to do this, but these steps will always work. You'll first start by getting the 1 there. And then you will get the 0 below. I'll show you a way that you can always use the 1 to make the 0. And then once you have that, that's sort of the steps. So get the 1 in the top left, get a 0 below it, then get the 1 beside that, using these sort of strategies. So I'll show you what that's going to look like with this first one. So what I want to do is make a 1 in the top left. So I'm allowed to add or subtract rows. That's allowed. And I'm allowed to multiply a full row by a scalar. So that's normally what I look for. Is there a row that divides nicely? And I see the second row is all divisible by 2. So if I multiplied that second row by half, I'd have a 1 in the first spot. That's something that we want to happen. And then if I swap the rows around, I can put that 1 in the top right corner. So what I'm going to do is I'm going to write between what I'm doing. So I'm going to swap the rows. And then I'm going to do, well, maybe I'll write it as, just so it's not confusing, row 2 times a half. So divide everything in that row by 2. And then I'll swap the rows so that I know which row I'm actually multiplying by a half. And you can do kind of 2 steps at once like this, as long as you're sure that doing the first one doesn't change the second one or something like that. So I'm going to divide the second row by 2 and write it first. And then I'm going to write, since I'm swapping the rows, the old first row there. So there's my 1 in the top left corner. That's one way to do it. I could have, because of the way these are set up, I could have subtracted row 2 from row 1. That would have made a 1 in the top left corner. But that's sort of this way of looking for something so that you can kind of divide a row by something and make a 1. That's the way that's going to work most often, or hopefully you can do that without making fractions or decimals. So I'm just going to do sort of the default way and not a special way. So from there, I'll show you what I mean by these combos. So I'm going to replace row 2 because I'm going to try and make this 0. And what row 2 is going to become is I can add or subtract the 2 rows together, and I can multiply by scalars. So what I'm going to do, the trick is you get that 1 there first, because then you can always do this trick. Multiply the first row by 1 and subtract row 2. And I'm just changing row 2 when I do this. So I'm going to leave row 1 as is. And you're going to say, well, didn't you say you're multiplying row 1 by 3? And yeah, I will when I do the subtraction, but I'm not actually going to change row 1 because I want that 1 there. So just think of it as I multiply it by 3, do this operation, and then divide it back by 3 and change it back to where it was. So just changing row 2. So I'm going to go through and make sure I'm doing it right. 3 times row 1, so that would be a 3 in the start. 3 take away 3 would give me the 0 there. That's good. 3 times the first row would be 6. I'm subtracting -2. I'm going to get an 8 here. 3 times row 1 would be -3. I'm subtracting 1 more. I'm going to get -4. 3 times row 1 is -18. I'm subtracting the 7. So I'm going to get -25, I believe, there. So that's sort of 1 in the top, then 0 below. And then the last one is change that 8 to a 1. And the way that's always going to work is we're going to take row 2 and basically divide it by 8. Multiply it by 1 over 8, however you want to say it. So 0 divided by 8 is 0. 8 divided by 8 is 1. 4 divided by 8, well, it's a -4. I could say -0.5 or -0.5, and I can do -25 over 8, or change that to a decimal if I so choose. I like fractions. And then we're done, which is super weird, but that's what I said the goal was. A 1 in the top left, and then the next row starting with a 0, then a 1. That was my overall goal, and I'll show you why that's my overall goal. Because we know we have a line of intersection. So our line of intersection, think about our final answer is going to be a bunch of parametric equations. And remember, you can choose any point on the line for the starting point, and you can choose any direction vector as long as it's a scalar multiple of the actual direction of the line to get the line. So line equations can look very different, I guess is what I'm saying. So we have some choice in this matter. And I'm going to choose to let z equal k. So once you get it to that, you typically say let z equal k, where k is some real number. So my parametric equations is going to be z equal k. So if I'm thinking about this, I'm just making it, since I can choose any point, I'm choosing the starting point with a z of 0. There will be one on this line, and I'm scaling the direction vector so that it's got a 1 in the z coordinate. So that's sort of how I'm setting this up. Now with that, row 2 becomes, so remember this was x, this was y, this was z, this was an equal sign. That's how we changed it into a matrix. Row 2 now becomes no x's, 1y, minus 1/2 times z, which we just turned into just plain old k for our equation, equals -25 over 8. And so it's really easy to get my parametrics for y, -25 over 8 plus 1/2 k, something like that. There's my parametrics for y. So there's no real solving to do there. I'm just moving the half k over. There's my parametric equation for y, which equals negative 25 over 8 is the starting point coordinate. 1 over 2 is the scalar multiple, so that's the vector component there, sorry, for the direction vector. Now, you can just write the 3 parametric equations when you're doing these. You don't need to write it in both forms. I'm just kind of showing you the pieces both ways. And once you have row 2, row 1 looks like 1x plus 2y's. Oh, we know what y is. It's minus 25 over 8 plus a half k minus a z, which we said is just k, equals negative 6. So the only thing left is x's and k's. Just keep it separate. We're just going to solve for the x. So x is going to equal, I'm doing, that'll become negative 50 over 8. So I'm going to put that to the other side, positive 50 over 8. That will become 1k, oh, minus a k. So the k's actually just go away. That's neat. Alrighty then. So that's all we have to do, is just get that down to a number. So 6 would be, what's that, 48 over 8. So 2 over 8, so a quarter, I think. So x is just 1/4. So its parametric equation looks like 1/4 and 0. So that's the equation of our line of intersection. So it's not moving in the x direction. It's kind of vertical through there, which is neat. Okay, in a sense. So that's how we find a line of intersection when we have two row matrices, two planes. So here's my next example. You can see I have much less room to do this one, and that's on purpose, because I'm looking at my direction vector, or sorry, my normal vector, and I see that this is times 2, and this is times 2 and matches, and this is times 2 and matches, and this is not times 2. So these equations are in fact different equations, because the first one would change to 2x plus 8y minus 6z plus 12 equals 0. And that's a different equation. It's a different plane than the first plane. But since their normal vectors are scalar multiples, so a, b, c are scalar multiples, but d is not. So their normal vectors are going in the same direction, but they are different planes. Therefore, we know that these are going to be parallel planes. And there's going to be no solution. So again, we're going back to these pictures. The normal vectors are in the same direction, but they are different planes. So it's picture 2, not picture 3. If all 4 things were scalar multiples, if the a, b, c, and d all matched by the same scalar multiple, then they'd be the exact same plane. And we'd say these planes are coincident. And the whole plane is the same. The whole plane is the solution. That's what I'm trying to say. Whew. Okay, so that's sort of our appetizer course of this lesson. And we're going to move into 3 planes. So this is where it gets fun. 3 planes can interact. Didn't plan that out very well. In 8 ways. So you can pause the video, use your desk as one of the planes, use 2 pieces of paper as the other 2. See if you can find all the ways that 3 planes can interact. There are 8 different cases. And when I talk about solutions, I'm talking about points that are common to all 3 planes. So if a point's on 2 but not the 3rd, it's not going to count as a point of intersection of the 3 planes. If it's going to be a point of intersection of the 3 planes, it has to be on all 3 planes. Okay, So pause, see how many of the 8 you can come up with, and then I'm going to start to fill them in. So I normally start with the most boring. Is I could give you 3 coincident planes, and then it would be infinite solution. The whole plane would be the solution. So I could give you 3 equations that are in fact the same equation. I could give you 2 coincident planes and leave the other one as a parallel to those 2. So 2 of the equations are exactly the same. One is same ABC or scalar multiples on the ABC, but D is not a scalar multiple. As soon as you have that one plane that's not touching the other 2, there's going to be no solutions. So, yeah, there we go. I could give you 3 parallel planes, and that would have no solution. None of them would touch each other. I could give you 2 parallel planes, and then the last not parallel. So if I look at sort of the side view, we'd have 2 planes that aren't touching, completely parallel. We'd have the third plane that sort of cuts through both of them. So there'd be, like a line of intersection going through. So these are, that's just looking at the very edge of the plane, but imagine it's stretching forever, like through the page. There'd be a line of intersection going down there. There'd be a line of intersection between those 2 planes, but there's no points that are on all 3 planes. So we can right away say that there's no solution. Because as soon as you have 2 planes that don't touch, then for sure all 3 planes won't all touch at the same time. So no solution there. Is that the one more weird one? 2 coincident planes. So 2 of the equations are actually the same, and then the third is not parallel. Well, as soon as you have 2 coincident planes, really it's not a 3-plane problem. Really it's a 2-plane problem, because 2 of them are the same plane. And if they're not parallel, then you're going to get a line of intersection. And now we get into the cases that are actually interesting. So we can have 3 planes all meet at a point of intersection. That's something that can happen. So you could have, say, one plane doing this, one plane, say, doing that. Let me try and draw that better. Something like that. And then, say, the third plane lying down here, and they all meet at that single point of intersection. There's one point that are on all 3 planes. And maybe that seems unbelievable, but think about the XY plane, the YZ plane, and the XY and the XZ plane. I think I got the 3 main planes that we started with, and when we first started talking about 2D, those 3 planes, the only point that's on all of them is the origin. So that is a point of intersection. My next one, I call it the book. And that's where, imagine the planes are all meeting on a single full line of intersection. So you have a line of intersection, and you have the planes all sort of meeting that line. And I call it the book because I imagine the planes being 3 pages of a book, and the line being sort of the spine of the book where they all adjoin. That's one way to picture it. Keep in mind the planes would go kind of on forever in all directions, so it wouldn't quite look like a book if you drew the full thing. It would look more like, say, an asterisk in space. So some people call it the star. I like to think of it as a book and just think of half the planes at a time. And my last case, I call it the tent. But really it's kind of like a triangular prism. So the planes kind of form a triangle in space, so I call it the tent. So these lines, so those 2 planes cross at that line, those 2 planes cross at that line, these two planes cross at that line, but not all, those lines never cross. So there is no solution when it's the 10th. There's no points that are on all three at the same time. So it's a kind of like a, they'd form a triangular prism. And so the edges along the triangular prism would be the lines of intersection between two planes at a time, but we would say that there's no solution to the three-plane problem. There's no points on all three planes. So that's all the things that can happen. Cases 1 through 4, the way I have it written out, all involve no work at all. You can figure out those cases just by looking at the A, B, C, D. If A, B, and C are scalar multiples and D is not, then those two planes are parallel. If all four things are scalar multiples, then they're coincident. And you can figure out which of the four cases you have based on what combos of that you have. And then you don't have to do any work to get to the final answer. This one is really a two-plane problem like the one that we just did. So you're going to do a two-row matrix. If you have two planes are actually the same, you just throw out one of the copies of the same equation and work with two rows in your matrix. And these three all become a three-row matrix. And we got to row reduce a three-row matrix. And what happens in that kind of determines which of the three cases we have. So with the three-row matrix, our goal is still have that 1 on top and just any numbers after it. The second row is going to be 1, 0, and then the third row 0, 0, 1. That's our goal. So our goal is to turn the matrix into that. My robot order to get there is get the 1 first. It's a lot of number signs. And then get 1, 0, 0, and the rest of the matrix. I don't know why I didn't do that the first time. And then get 1, 0, 0, get the 1 there next. And then get the 0 below. And then your last step is get the form that you want. So turn that last number into a 1. So that's kind of our robot order that we're trying to get. Now, three things could happen, right? We could have a point of intersection. You could have the book, a line of intersection, or you could have the tent and no intersection. So what's going to happen is if you get the goal, if you get this, then you have a point of intersection. But if this happens, so as you're going along and you're trying to get that set up, so you've got this far, and you have the 0 there, and then so you're basically at this step here. When you get the 0 here, what happens is this also becomes 0. And if this also becomes 0, really what happens is you try and get the 0 there, and then the rest of the row just happens to 0 out. Then you're dealing with the book, and you've got a line of intersection because it's like this third row is all zeros, it doesn't count. And you're left with just a 2-row matrix like we have above. And it is the goal for the 2-row matrix. You'd have the setup of 1, 0, and then the 1 below. So from there, you're kind of done. You let z equal t, and you get the line of intersection from there. And then the other thing that could happen, if this happens, you have this set up. You get the 0 there. When you make this 0, this goes 0, but this number doesn't go 0. So the x, y, z are all 0, and the last number is not. And that turns into the equation, that bottom row, 0 equals 5 or something like that. And that's one of those equations that's just not true. It can't happen, which means that there's no solution. And if we've gone into the matrix, right, we know that we have either point of intersection, book, or the tent or the triangular prism. No solution. So that's the case in the matrix where you don't get a solution. So if you get that 0, 0, 0 equals 5, well, then you know that there is no answer, and it should look like the tent when you draw it out. Well, I won't make you draw it out, but that's what you'd have. So here we go. I've already moved the d values over. I'm going to look for scalar multiples. So if I look at the second one, if I times it by 2, it matches the x's, but the y's don't match when I do that. So the first two aren't parallel or anything like that. When I do x times -3, the first one matches, but again, the y's don't match. So no scalar multiples there. And if I look closely, no scalar multiples between the first two. So there's no scalar multiples. No scalar multiples. We just switched colors, which means that we have to enter the matrix. Okay, so I'm going to set up this matrix. I know that my first goal is to get the number 1 in the top left corner. So I see that that one has a 1, so I'm actually going to just save myself some time and write that one first. If I wrote it the other way, I'd just swap the rows as my first move. So I'll just write it basically without the letters. Again, I wrote Z. That should be a 1. The d value is already on the other side, so we don't have to deal with that. There we go. So we have the 1 in the top row. Our next mission is to make zeros below that 1. So since it's a 1, sort of the combo that always works, multiply to match, and then subtract. So if I'm changing row 2, I need to use row 2. I can't use row 1 and row 3 and replace row 2. So I'm taking row 2, doing 2 times row 1, and then subtracting row 2. So row 1 is good. It's going to stay exactly the same for the whole time. And then I'm going to do 2 times row 1, which is 2, subtract row 2, which is 0. 2 times row 1, which is -6, subtract -5 is -1. 2 times row 1 is -4, subtract 1 more, -5. 2 times row 1, -18, subtract -3, -15. Now, to save myself writing out the matrix again, I can do the same thing with row 3, and as long as I don't use row 2, because I've changed row 2 now, we'll be good to go, and we're just going to use row 1 again. So I will do 3 times row 1 to make it match, but since the bottom's negative, I'll add row 3 to make my 0. So that's how I might handle that one. Or you could multiply by -3 and then subtract row 3, but that's too many negatives for my brain to handle, so I'm going to do it this way. So 3 times 1 is 3, add -3, we in fact get 0. 3 times -3 is -9, and then add 6, we get -3. 3 times -2 is -6, add 2 is -4. 3 times -9 is -27, add 8, -19, I believe. So there we have our 1, 0, 0. Sorry, we have our 1 with the 2 zeros below. So our next goal is to change that to a +1. So we're just going to multiply row 2 by -1 just to switch it to a +1. So row 1 is going to stay the same. Row 2 is going to stay the same. Sorry, row 2 is going to change to all positives now. Row 3 is going to stay the same. So we have that now. Now, we want to turn this to a 0 next. Now what's going to happen is it's going to be really tempting. If you look at row 1, it's got a -3. It's going to be really tempting to do row 1 minus row 3, something like that, to make a 0 there. You don't ever want to use row 1. Once you set up your 1, 0, 0, stop using row 1, because if you end up subtracting, you're going to put, you're going to change that 0, because you're going to do 1 minus 0 or 0 minus 1, whichever order you do it. You're going to ruin that 0 that you worked hard to get. So once you have the 1, 0, 0, you're now going to use only row 2s and row 3s. So I'm going to do the same thing. I'm going to take row 3. I'm going to make a match by doing 3 times row 2, and then adding row 3 will make the 0 with the signs as they are. So row 1 stays like that. Row 2 stays like that. Row 3, now we got to do the math. So let's check. 3 times row 2, 0 times 3 is 0, adding 0, this stays 0, that's good. 3 times 1 is 3, add -3, that's 0. 3 times 5 is 15, add -4 is 11. 3 times 15 is 45, and then subtract 19 is 36. Does that seem right? No, 26. Yeah. I thought I got whole numbers here. I'm just going to pause and check to make sure I haven't made any mistakes. Okay, so I didn't make any mistakes. Just double checked. I was just expecting something divisible by 11. But our last step is going to be row 3 divided by 11 to change that into a 1. (26/11). That's pretty annoying. Okay, so we actually accomplished our goal. So we have a point of intersection. And that last row tells us that Z equals 26/11. No x's, no y's, 1z equals 26/11. So once we know Z, we can use row 2 is set up to find y, so you kind of work your way from the bottom of the matrix back up to the top. So row 2 says y plus 5z, which is 26/11. I'll erase that because I screwed up this calculation and had to go back and redo these steps. Y plus 5z equals 15. So that's y plus 26 times 5 is 130/11 equals 15, which is 165/11. That's what I screwed up last time. So y equals, when you subtract the 130 from both sides, 35/11. So we've got 2/3 of our point figured out. To get the x, you go up to row 1. Row 1 says x minus 3y's, which is 35/11, minus 2z's, which is 26/11, equals -9. So x minus 105/11 when I multiply by 3, minus 52/11 is going to equal -9, which is -99/11. So on the left side, I've got -157. I'm going to add that to the -99 on the other side. I get 58/11 for my x value. So that's going to fill in, and that's my super annoying looking point of intersection, but at least it's done. So there we go. So that's my first example. All right, so I got some practice for you. So 3 examples for you to try. If you load up the PDF on the classroom, I've got a link to an online calculator that does the row reduction for you, and a video I made last year showing you just how to use that online calculator just to help catch any minus sign mistakes or something like that. That's actually what I jumped to and used when I got the 26 there. I just double checked in that calculator that I hadn't made any mistakes, and it'll show you step by step the row reduction. but also pay attention to, do you actually need to go into the matrix? So look for those scalar multiples first and see if you have parallel or coincident planes involved, and see if you can get the answer without doing any work. So lots of different examples there. I think almost all my examples start with 3 planes. I think one of them at least has where 2 planes are coincident, and the third's not parallel, so you have to do the 2-row matrix thing. But for the most part, 3-row matrices, there's tons of practice there. You don't necessarily have to do all of them, just do enough that you've practiced these steps and can make your way through one of these on the test.